We have Timo here. He'll be presenting on dynamic flash instrumentation for fun and for profit. So please join me in welcoming Timo. Take it away. Thank you.
Thank you. Can everyone hear me okay? Can you still see me if I stand here? Okay, we're all good. Welcome all. It's great to have you here. Thank you. Thank you for coming. This is actually my first time attending Black Hat. So I'm extremely honored and humbled to present you dynamic flash instrumentation for fun and profit. Today, we are releasing a new open source tool called Sulo. As far as I know, Sulo is the first publicly available tool that you can use for dynamic analysis of flash files. And the goal of this presentation is to share the things that I learned while I was building that tool. And the structure of the presentation is quite straightforward. First, I'll explain you why I strongly feel that there is a need for such a tool. Then I'll show you some of the previous research that was extremely helpful in building this tool. Then we'll briefly discuss internals of the Flash player. And then finally, I'll show you some demos with the tool. So I'll be analyzing 4 different malicious Flash files using the tool. So the motivation. Why do I think we really need such tool? Typically, when I analyze Flash files that are potentially malicious, I use a decompiler. If the decompilation is successful, the analysis is pretty easy because you get the ActionScript source code. However, if the Flash file is obfuscated, or if there's some sort of encryption, or if it uses some commercial protector, things get tricky. Static analysis isn't impossible, but it's going to take a lot of time. Let me show you some examples. I'll start with the most basic obfuscations and encodings and encryptions, moving on to more difficult and complex ones. And the first 2 examples that I have are from APTs. Here's the first one. This is a snippet from the Flash exploit that was used in the RSA attack. This was 0-day at the time. And as you can see, it's pretty straightforward. There's not that much obfuscation. Those are the first 3 bytes. That's CWS, marker for the compressed Flash format. So there's really no obfuscation, just hex representation of the embedded Flash object. And like with the majority of Flash exploits, the embedded Flash object is loaded using this load bytes method call. There are other ways of loading embedded Flash objects, but this is by far the most common. So if you consider this an APT, at least from the Flash obfuscation perspective, there isn't really anything advanced. Another similar example, this is from Cosmic Duke, the attacks connected to the Mini Duke group. I have to say that I find this funny. These guys really use some imagination. Again, no encryption, just a really exotic encoding scheme. You have the string win, and the number of letter i's varies from 0 to 15. So that encodes 1 nibble, and then that's turned into binary, and then again loaded using load bytes. It's a really weird encoding scheme, but hey, it might actually work against some antiviruses. I don't know. This one I wanted to include as a reminder that when I talk about malicious Flash files, I'm not talking only about Flash exploit, but also about malicious redirectors. This one was found on YouTube. This is from a malicious YouTube ad that redirected IE and Opera users to Styx exploit kit. And this is the interesting part. The call method in external interface. You can use this one to execute JavaScript in the browser. And again, the parameter, that's just the JavaScript string. And in this case, it's both encoded and encrypted. Normal ASCII hex first, then conversion to binary, and XOR with single byte XOR key. Nothing too complicated, but as you can see, it keeps on getting more complicated. If you do all this manually, it takes more time. Now there's already 2 steps, the encoding and the encryption. Still quick with static analysis, but not that fun. This one is from Fiesta exploit kit. In this case, the Flash object is constructed from an array of integers. Again, if you copy those values, you need to do some formatting. It's slower, and there's also simple XOR encryption. The other things that's really interesting about this one is the way it calls load bytes. And this is a good reminder of how Adobe Flash Player works. So let's say you decompile this file, you open the action script in some text editor, you do Control F, load bytes, no hits. Another reason why it's important to realize that the method name can be generated while the Flash is running is that that's probably the most simple way of obfuscating the method name, just splitting the string. But I mean, you could do encryption, you can do anything. So this is what makes static analysis challenging. Finally, by far the most challenging thing to deal with static analysis are these commercial protectors. And one of them is do-swift. This example is from Flashback exploit kit. In this case, the embedded object is defined in the define binary data tag, so it's inside the Flash file, and it's loaded and decrypted. And this same protector has been also used by the Elderwood group in some APT attacks. They didn't use Flash exploits, but the Flash that was responsible for the heap spray used this do-swift protection. The holy grail of Flash protection, in my personal opinion, is secure Swift. Let me demonstrate. This is a file from Angular exploit kit. And let's start with the class names. The class names are obfuscated. So you can imagine the headache when you start reverse engineering this, analyzing this statically. It's a pain. Again, the embedded Flash object is encrypted. There's at least 2 possibilities, AES and RC4. If you need to decrypt something, you need to get the input data and also the key. In this case, the algorithm is RC4, and the key is generated on the fly. Obviously, it's always the same, but it's generated on the fly. So you cannot find the key as a string or byte sequence anywhere in the Flash object. And this is how the key is generated. So that's 1 byte and that's another one. And these are not even in order. So if you want to know the right order of the bytes, you need to also evaluate the expression there. So imagine doing this manually. If you compare this to, let's say, Windows malware, PE malware, if you see something that's clearly packed, what do? You're not going to stare it in IDA Pro. You're going to run it. So obviously that makes sense with Flash too, but if there's no tools for dynamic analysis, you cannot really do it. So that's the reason why I strongly felt that it's worth building this tool. And I had 2 goals originally for the tool. First one was to be able to intercept these external interface calls, so the ones used by the Flash redirectors. So you can get access to the JavaScript. But clearly the more important goal was to be able to get those Flash objects that are loaded with load bytes and dump those to disk. Because if you can do that with, for example, do-swift or secure Swift, your job is a lot easier. And I will demonstrate that later. When I started building this tool, I can honestly tell you that I didn't know anything about the internals of Flash Player. I had analyzed many malicious Flash files, so I was familiar with that stuff, but I didn't really know that well how Flash Player works. So for that reason, I really strongly feel that with this research and this project, I'm standing on the shoulders of giants. And I want to take this opportunity to both thank these researchers and also promote the research that they've done. Because if you're interested in this kind of stuff and you haven't seen these presentations yet that I'm about to mention, you should really check those out. Really cool stuff. And I'll start with Matt O. Is Matt in the audience? Yeah, can you stand up, please? Let's give a big round of applause to Matt. Matt is an impressive guy. He has done at least Java exploit analysis and presented that in Black Hat. Flash exploit analysis, he's the father of the Darren Grimm diffing tool. And this year he presented about analyzing Flash memory. So the Flash, physical Flash memory, not Adobe Flash. So impressive skill set. Here's one of Matt's presentation. This is from ShmooCon 2012. Matt can later correct me if I get this wrong, but I think he presented two different methods for instrumenting Flash files. The first one was about modifying the Flash object itself by adding new stuff, new code that essentially hooks the Flash file. The second one, the approach was called class hooking, and the idea there was that all classes are resolved by name during runtime, and there's an array for that. So if you modify that array, instead of loading the original class, you can make the Flash player load your own instrumented class. That's a brilliant approach. And when I saw these slides, I was like, yeah, it seems that Matt already solved this problem. So I sent him a direct message on Twitter and asked that, hey, did you ever release the tool? And unfortunately, he wasn't allowed to release it back then, so I thought that, okay, there's still need for such a tool. I also want to thank the Adobe ActionScript 3 team, because the engine that Flash Player uses for executing ActionScript, called Xamarin, has been released as open source. So you can imagine how much easier my work was, because I didn't have to reverse engineer everything. I had at least some source code available, which was very helpful. When I started doing this, when I started building the first prototype, there was two key questions that I had to be able to answer in order to build something meaningful. And the first one is really obvious. Where are the ActionScript methods called from? If I want to intercept a method call, I need to know where it's called from. And Xun Feng, he's a researcher with Microsoft, he was extremely helpful. When I mentioned him that I'm about to build a tool like this, he was like, yeah, that sounds cool. And he kept on sending me emails and links to all great Flash presentations. And he even shared a WinDBG script that he had written for a specific Flash version for dumping the embedded, or dumping the Flash to disk that's loaded with load bytes. But that worked only with a specific Flash version. But in any case, that was a great starting point. So yeah, I'm really thankful for his help. He has given multiple presentations about analyzing Flash stuff. And this is from Caro Conference 2011. And I found two really interesting things. There's a lot of good stuff, but these are my favorites. How many of you are familiar with this configuration file? Hands up. One, I think. Okay. This is a configuration file for Adobe Flash Player. It has all sorts of flags that you can set. The most useful for me was this AS3 trace. And this is a screenshot from a blog post by Jean-Paul Leclerc. The URL is there on the upper right-hand corner. You can check it later from the slides. If you are running a debug build of Flash Player, those are publicly available. And if you set this flag in that configuration file, you can see all the ActionScript methods that are called. And that by itself is already very helpful if you're analyzing something you haven't seen before. For me, this was helpful because I knew that, okay, Flash Player is able to do that. If I figure out how it does that, I'll probably figure out where the methods are called. This was also a great benchmark when I built different prototypes. If I wanted to see that, okay, do I now see all the method calls? I just calculated that how many lines are there in this log produced by the Flash Player and then compared to my own count. And if it matched, then I knew that, okay, we're good. And from this, I got already pretty far, especially with the help of this thing. This is the other thing from June Frank's slides. He mentions that all the ActionScript methods that are generated by the just-in-time compiler are called the same way. All those ActionScript methods are called the same way, and that's how they are called. It's just 3 parameters, really straightforward. And with this information, I was able to build the first prototype, and I saw all the method calls that were visible in Adobe's own logs. The challenge was that I had some duplicates, and I couldn't figure out which one was the right one that I should be logging and which one was the extra one that I should get rid of. I tried to come up with some sort of filtering logic, and I thought of different places where I could instrument the code to solve the problem. But to be honest with you, I hit a brick wall. I was like, I don't know what to do. So I went to the source code of Xamarin, and I Googled some values, and I ran into one of Hai-Fei Li's presentation. You've probably heard of Hai-Fei Li. I won't introduce him. And this is the presentation from Recon 2012 inside AVM, ActionScript Virtual Machine. And in these slides, this is a direct quote, hook at the end of verify on call. And that's what I did. And spoiler alert, doing this solved my problem. I got rid of the duplicates, and after that it has been really robust. So big thank you to Hai-Fei Li. Let's go into details. If you want to see the ActionScript method calls, you are probably interested in the values of 2 different function pointers for each method call. So 2 function pointers for each method. First one is the highlighted one, invoker. That's used for the methods that are executed by the interpreter. And the other one in the union, that's the one used for those methods generated by the just-in-time compiler. So if you can somehow figure out the values of these 2 function pointers for each ActionScript method, then you're good to go. And what Hai-Fei Li said in the slides, hook at the end of verify on call, let's look at the details. This is verify on call. Can you see this at the back? Is the font large enough? Okay, it's good enough. Here's the first one. Right at the end of the function pointer to the JIT code is set. For the interpreted functions, you need to follow the verify method call, which leads to verify interp, again leads to set interp, and that finally sets the other function pointer. In other words, by the time you get to the end of verify on call, both of those function pointers have been set. So if you instrument there, you can check the values of those function pointers and you're good to go. Now the challenge is that we know how this works on the source code level, but how about the binary? How do you find the right spot in the binary or in the memory? Well, the good news is that with the debug build of Flash Player, you have some extra code and some extra strings. So if we go back to the verify interp function, there's this exec policy interp string. So if you just go to IDA Pro, open the debug build, list the strings, you can find the string, and after that it's easy. You can find all these methods that I just showed you. And yeah, there's the verify on call method, and then you just hook at the end. Now some of you might have realized that I didn't actually answer my original question, which was that where are the ActionScript methods called from? We know where those methods are, but we don't know where they are called from. Well, is this relevant? It depends. If you want to know the return value of those methods, and you probably will, you have basically two options. Either you need to know where's the end of the function, or then you know need to know where the call is made, so you can then check the return value. The first version of my tool is built using Intel pin, and at least I don't have the skills to use Intel pin so that you would find the function end. I'm not sure, is it possible? Might be. So the only realistic option was to find where the call is made from. That's easy on runtime. You just check the stack. On top of the stack, you will have the return address, so you know where you should instrument. However, with Intel pin, it's not that straightforward. There's a method called rtn_create@. And you can use that to say that I have this address, instrument at this address. The downside is that that function works only for code that's part of an executable image. And the code that gets generated by the just-in-time compiler obviously isn't a part of any executable image. So you can actually use that. So what I ended up doing was instrumenting all potential method calls, and then at runtime when the call happens, I check the target of the call. And if the target matches the values to one of those two function pointers per method, then I know that, okay, this is an interesting call and we should also instrument the return address. That was the solution. And that was just to overcome limitations of Intel pin. I mean, if you use traditional hooking, it wouldn't be a problem. The second key question. Now I see all the method calls, but I have no clue about the name of the method call. Doesn't really help much. Yeah, I got 600 method calls. I don't know what those are. Doesn't help much. So, how to get the method name? Again, we come back to this one. The first parameter, pointer to method env object. And method env has a member called method info. Now, if you're interested in this kind of stuff, and if you want to start researching this, start from the method info class, because it's all built around that in some way or another. So that's a good place to start. In method info, there's a method called getMethodName. Looks promising, right? Probably gives you the method name. That's the whole function. Not that much code. The bad news is that there's another method called to getMethodName with traits. And that one is a nightmare. I still have nightmares about that. Well, no, not really, but it's pretty bad. Let me explain you. When you want to know the name of the method, you already know two things. You know the ID of the method. That's simply an integer. You have the ID of the method, and then you have an array of pre-computed names. And in that array are all the method names. So now you just need to map the method ID to an index to that array somehow. That's what you need to do. With debug build of the Flash player, it's really easy, because in the pool object, you have an array called method name indices. And from that array, you directly get the mapping, so you get the missing link. Unfortunately, with the non-debug build, that's the one that all the normal people are running on their machines, there is no such array. And the explanation is in the comment. I mean, it's not always populated. So with the normal non-debug build, what I had to do was manually build that array. And it wasn't really as easy as I would have hoped for. What I had to do is parse the code of the Flash object, because you get that information from the Flash object. The good news was that Xamarin has already implementation for that. It wasn't really just copy-paste, because there's so many special conditions and all that stuff, but if you need to do something similar, check the source code of parse method infos and you can find it. That's where the magic happens. I'm from Finland, and in Finnish we have a saying, nälkä kasvaa syödessä. The direct translation would be something like, the more you eat, the hungrier you get. And what I mean by that is that when you are building a new tool and when you add a couple of features, you want to add some more. And that's exactly what happened. So when the original goals were already met, I started thinking that, okay, it would be nice to log all the arguments of the method calls and also the return values, which is pretty obvious because if you can do that, you already have a lot of information. You have a full call trace. You might remember from the log that Adobe Flash Player generates is that there's only the method name, no parameters, no return values. This is easy in a way. Again, we get back to the way all ActionScript methods are called. There's 3 parameters. The middle one is the argument count, and the last one is the argument pointers. The first element in that array is the this pointer, pointed to that object itself, and the rest are the arguments. The return value, well, it's the return value of the native function call, so you will find that in the EAX register. Quite straightforward thus far. The only challenge is that if you want to have some meaningful logging of these values, let's say that you have a function and it takes one parameter and that parameter is a string. If you just log the values from that array, all you have in the logs is a pointer. And you would probably want to have the actual string in your logs. For that, you need to know the types of the parameters and the type of the return value. And again, I have to say that this wasn't as easy as I wish it would have been. The good news is that Xamarin has the source code. It's the same parse method infos method I mentioned earlier. That one, at that point, it reads the type of the return value, and then there's a loop for reading the types of the parameters. If you do that, you eventually get all the type information. A couple of words about the design of this tool. This one I'll keep really brief. Open source for the win. It was obvious that if I'm able to build this, I will release this as open source because at least I think I'm not the only one who has to deal with the problem of analyzing do Swift protected stuff or secure Swift protected stuff. So yes, today this has been released as open source. Like I mentioned, this is built on Intel Pin dynamic instrumentation framework. Now for those asking why Pin, why not something else? Pin has a nice API and it was really, really helpful and easy in the beginning, in the research phase. For example, if you want to instrument all call EAX instructions, that's trivial with Pin. It's really easy. Later I found out that okay, there's some limitations in the API, and now that I have the first prototype, I probably want to go with normal hooking with the next version, because there is some performance impact with InsoPin. But I want you to keep in mind that when I started building this tool, it was designed to help manual analysis, and it can already be used for automatic analysis in the backend. There is a performance impact, but if you have time for analysis, it doesn't really matter. The only place where it matters is if you would need to do real-time analysis on the client. That you cannot do yet, but perhaps with the next version. And finally, I have something called plugins in this tool. Now, if somebody is a software architect or software designer, they would surely say that that's far from a plugin architecture, and yeah, I agree, it's really far from that. This is poor man's plugins, as simple as it can be. If you want to write your own plugin, you just need to do two things. You need to override 2 virtual methods. The first one is called before each ActionScript method call. And with that method, you get the full method name, you get the argument count, the arguments, and also pointer to the method info object. That should be more than enough information. And the second virtual method you need to override is the one that's called after the ActionScript method call. And that one gives you the return value. So as you can imagine, if you get all this data, you can do all sorts of things. And with the first release, there are 3 plugins. First one generates the call trace where you can see all the method calls, parameters, return values. The second plugin is responsible for dumping all the Flash objects that are loaded with load bytes. And the third one is something you can use to decrypt the strings that the secure Swift commercial protector uses. And I'll demonstrate all these plugins in a minute, which is now. And since we're in Vegas, I decided to take a walk on the wild side and use Windows XP and IE6 for my demo. I like to live dangerously. Okay. I'll start IE with the instrumentation on. So technically IE isn't instrumented in any way. It's the ActiveX Flash player that's instrumented. And I'll start with the redirector sample that I showed earlier, the one that was found on YouTube, redirecting people to Styx exploit kit. This is a really simple example, but I want to use this to show you the kind of information that you can get from the call trace. Okay, it's loaded, all good. And that's the normal log, there's nothing interesting, but here's the call trace. So here you can see that you can also see what method called which method, so there's this kind of call tree. Now if you're interested in knowing that what was the JavaScript that was injected to the browser, you want to find these external interface calls. The first one here, it simply, for some reason, uses JavaScript to check the user agent. You could do that directly from Flash, but yeah, it uses JavaScript. And the second one then injects the malicious JavaScript, doing the redirection to Styx exploit kit. So let me get that list again. And I'll enable word wrapping. And here we have it. It creates an iframe, and that's the URL. So now imagine that you're a researcher like me, and your task is to first figure out that is this Flash file malicious, and if it's a redirector, what's the target of the redirection? Well, there you have your answer. All you needed to do is just run the Flash file. If you did this with static analysis, you had to decode and decrypt. Okay, that takes 3 minutes, but this takes only 2. So this is still better. Okay. For the next demo, I'll disable the call tracing. I'll run it in something I call fast mode. It's a stupid name, but that's what it is. It's a fast mode. It's faster. So the only thing that now changes is one command line parameter to my tool. That's the only change now. And the next demo is with an exploit. If you use the call tracing with exploits, especially if you have heap spraying with lots of loops, you end up with some pretty large call trace files. One was 500 megabytes. So yeah, don't do that. And I'll start with the one from Fiesta exploit kit. So now it's in the fast mode. Call tracing is disabled, but the Flash dumping is still enabled, and also all other plugins except the call tracing. Okay. Loading. And here we have something. That's this is the Flash object that was loaded using load bytes call. We can scroll down a bit, or better yet, let's take a copy of the source code, open it in Notepad, and we can search for something like this. Yeah. And there you have it. If you want to know what was the vulnerability exploited, there you have it, CV 2014-0497. And remember that this embedded Flash object was constructed from an array of integers that was then XORed and then loaded. So again, I would argue that, yeah, faster than static analysis. Moving on to the ones protected with commercial protectors. And when I say commercial protectors, I don't mean that the attacker actually paid any money. I've seen the demo version of DoSwift used quite commonly. So let's try one of the DoSwift protected samples. Next, it's this one. And if all goes well, this time we should get 2 Flash objects, and we did. I'll open the first one. Okay, here's the good stuff. It has a shader object, and it clearly has shell code. So now we already know that, yeah, this is clearly malicious. If you see a shader object, most likely it's exploiting CV 2014-0515. If you want to confirm that, you probably check the define binary data tag. But in the first file, there's no define binary data tag. But the shader needs to come from somewhere. And that's the purpose of the second Flash file. And the way these 2 Flash objects are loaded is that they have the same loader contexts. So for the Flash player, it looks like it's one Flash file just simply split into 2. So it looks like one Flash object. And now, if we check the content of that define binary data tag, we can see that, yeah, it's a shader object, and if you look at it closely, you can see that, yeah, it's one that triggers the vulnerability. So, yeah, I like to remind you that this was a DoSwift protected file, also the same protector used by the Elderwood group. So, yeah, much easier with static analysis. I'll delete the dumped files, and now we'll go after the holy grail of Flash protectors, and that was the secure Swift. I'll use the same sample from Angular exploit kit that I quickly showed you earlier. This is the same file. With this one, IE will crash because it would like to get a parameter that defines the URL of the payload, and I didn't specify anything meaningful, so at some point IE will crash. And once it crashes, the analysis is done. Here on the desktop, again, we have the dumped Flash file, and as you can see, also the embedded Flash file is protected with secure Swift. And that kind of sucks, but what can you do? I'll copy the source code, paste it here. If we want to know the vulnerability, again, we'll do something like this. Yeah, it's the same vulnerability that we saw earlier. But I happen to know that this one exploits 2 different vulnerabilities. And to identify the other, I want to be able to decrypt the strings that the secure Swift protector has encrypted. And to do that, I need to find the string decryption routine. And what Flash exploits typically do is they check the version of the Flash player. So let's try that one. Yeah, okay. Here we have the version check, and the version string is saved to this .version. I'll search with that. And here's the good stuff. a long if comparing the version string to something coming from a function that takes an integer as a parameter. And I bet that the function that we see there, that's the one that decrypts the strings protected by Secure Swift. So what you can do with the Secure Swift plugin is you can take the method name and then you just change the command line parameters. So this is the patch file I used to load IE. And there's the fast switch. I'll add another switch, Secure Swift, and then you just give it the name of the string decryption function in the same format that Flash Player uses internally. And yeah, then you analyze the same file again. Let's see what we get. It would probably be possible to build that same plugin so that it logs the return values from all functions that take one parameter, which is an integer, and the function returns a string. That would probably give you more stuff, some false positives, but that might work as well. Then you wouldn't need to do this in 2 steps. I have written some Python scripts for statically decrypting these strings, and I can tell you that creating those scripts wasn't quick. So I'm happy that at least I have tools for dynamic analysis now. Yeah, here we can see the decrypted strings. Look at this, for example. Flash Player versions used for the version checking that we just saw. It also checks the Windows version. But how about this? This is the interactive part of my presentation. What is that? Yeah, regular expression. That's correct. And what's special about this particular regular expression? It's exploiting a certain vulnerability. If we go back to the ActionScript source, search for the integer that was given as a parameter, we can really confirm that yes, it is a regular expression, and that's the one that triggers the CV 2013-0634 vulnerability, also known as the Lady Boil exploit. Yeah. So now we know the 2 vulnerabilities exploited by this Secure Swift protected Flash file. And in my opinion, that's probably the best Flash protector out there, at least the best I've seen used with malicious Flash files. Okay. If you need to deal with analysis of malicious Flash files, I think you agree about the problem that, yeah, static analysis isn't enough, and hopefully you find this tool useful. If you're interested in how the Flash Player works, if you want to know more about the internals, you might be interested in the source code. I wasn't able to cover all the details in this presentation. Or better yet, if you want to contribute to the tool, here's where you can find it. So I must say that I'm really grateful to F-Secure because they let me release this. And the way it actually happened was that I first submitted to Black Hat, then I told that, yeah, I got accepted to Black Hat and I promised to release something as open source. And they were like, yeah, sure, that's a great idea. So they were actually happy to see someone wanting to release open source tools. So, I mean, yeah, I'm proud to work for F-Secure. That's all. Any questions? We should have time. Okay, thank you. Thank you. Do you speak English? You do? Okay. Any questions about the tool, the process, Flash Player, anything? Yes, please. Very good question. So the question was that, is my tool Flash player version specific? That's a great question. Yes and no. It was, from the beginning, it was designed so that it can support any Flash player version. Currently there are 5 or 6 different configurations supported, 10.x and 11.x, can't recall the exact version numbers. If you want to add support for a new version or different configuration of Flash, you need to specify a couple of offsets and related virtual addresses and stuff like that. So it should be straightforward. Yeah. Please. Thanks.
So I noticed that currently you're using Paint
Yeah.
for capturing the API calls, right?
Mm-hmm.
So I noticed that the execution is a bit slow.
Mm-hmm.
So is it possible to use other emulation tools like routines to implement a faster one?
Yeah. Very good questions. So the question was about the use of install pin and the impact on performance. So like most of you probably noticed, there's a noticeable performance penalty. And like I mentioned earlier in the presentation, this first version was never designed to be used for real-time analysis on the client. You could run that in the backend or use it for manual analysis. Partly because of the performance impact, but also because of the limitations in the install pin API, most likely the next version will be based on hooking. So the performance impact should be smaller. I don't know, will it be good enough to use it actually so that you can run it on the client in the background? Or is it still too slow? I don't know, but we'll learn. Let's see. Please. Mm-hmm. Yeah, the question was that would it be possible to modify the source code of the Flash player? Pardon? Yeah. The challenge is that for the actual Flash player, you don't have the source code available. So it's not really an option. You could probably do something if you just took the Xamarin engine and used that. I didn't want to modify the Flash file that's loaded in any way. I didn't want to touch that at all. I don't want to modify the Flash binary either, because my goal was that exploits should be able to run successfully in this environment. That's one of the reasons why I wanted to support the non-debug version of Flash Player instead of the debug version, even though that was easier to work with, but it might be that the exploit wouldn't work or the shellcode wouldn't run or something like that. So that's the reason why I chose to go with dynamic instrumentation. Any other questions? Very good questions. Please.
Is there a possibility that malware would detect that Sula is running and then like stop executing?
The question was that would it be possible for the malware or the malicious Flash object to detect that Sulo, this tool, is running? I believe there was another talk about detecting the presence of install pin in the process, but I think that was about native code, Windows malware doing that. Doing that from Flash, from ActionScript, if there's a bug in the tool, and most likely there is many bugs in the tool, by exploiting one of those bugs, it's probably possible. But if we talk about on the architectural level or philosophical level, it shouldn't be possible in my opinion. Yeah, very, very good point. But I have to say that if I see malware that tries to bypass my tool, that's a huge win for me. So yeah, I would be happy to see that. Any other questions? Great questions. One more.
So having the impact on speed of the analysis would be recognized by like a worker.
Yeah, Very good idea. That's a really good point. So the comment was that the malicious Flash object could use some sort of a timing attack to see how long the execution takes, and that way detect the presence of Sulo. Excellent point. That's absolutely true. Yet another good reason to use hooking instead of Intel pin or something similar. Okay, thank you very much for your time. Thanks.